Okay, so I know there's not very many slides, but packed in those slides is basically kind of pulling together all we've talked about. So have you ever like listened to severe weather and they'll talk about the stability of the atmosphere stable or the atmosphere is unstable? I don't know. That's what we're going to talk about, so we're kind of leading up to, if the air is unstable, that's when we get our thunderstorms. If the air is stable, then no thunderstorms. I don't know. So stable air in general basically means, we're talking about parcels of air here. We've been talking about parcels of air. We're going to keep talking about parcels of air, okay? In general, a parcel of air, the atmosphere, is said to be stable if that parcel of air of interest is cooler, more dense than the surroundings. So if it's cooler, more dense, it's going to fall. It's not going to rise, and we're not going to get clouds to form, blah, blah, blah. Now, if that chunk of air, the exciting one is the unstable, right? If that chunk of air is warmer than its environment, and we're going to, just like a hot air balloon, okay? If it's warmer than its environment, it's going to be lighter, it's going to be buoyant, it's going to want to rise. And as a chunk of air rises, its invisible boundary will expand, okay? And it will cool. That chunk of air will cool. We'll be talking about that. Okay. So I'm going to talk you through 3 different conditions that the atmosphere can be in. 3 different conditions of the atmosphere. Okay, 3 different types of stability of the atmosphere. We say that the atmosphere is absolutely stable. So notice I already kind of turned those words around. Hopefully you can get absolutely stable from absolute stability. Same thing, absolutely stable, absolute stability. We say the atmosphere is absolutely unstable, okay? Absolutely unstable. Or it's conditionally stable. Okay, conditionally means it could be either way. Okay, so this is all with regard to stability. So I told you we're kind of bringing things together, and we're definitely bringing things together. I told you for Unit 1 to basically tell me that the air cools 6.5 degrees for every 1 kilometer you rise. That's what I said. But I always try to condition that with you need to send up a weather balloon to know for sure. Okay? So we're going to be sending up some weather balloons here for some figures coming up. Okay? So it won't be 6.5 degrees cooling for every 1 kilometer you go up in the atmosphere. It's going to be something else. Right. So I'm also want to introduce you to something called, and it was in your notes in Unit 1, but I need to talk about something called a temperature inversion. If something's inverted, you think it's kind of topsy-turvy. Like at Adventureland, they used to have a ride called the inverter, and they would turn you upside down. Okay? So a temperature inversion means that the thing that's topsy-turvy is as you go up in elevation, instead of in the troposphere it getting cooler, it gets warmer. That's called a temperature inversion. And it has all kind of neat little ramifications in our atmosphere. But in the troposphere, if you go up and it's getting warmer, you are under the influence of a temperature inversion. Okay? All right. So let's take a look at an environment that's stable. So notice they sent up a weather balloon, and instead of it cooling 6.5 degrees, it's cooling 5. Right? So what does that mean? It means that this is the atmosphere. This isn't our chunk of air. This is the atmosphere. If they send up a weather balloon and the ELR is 5 instead of 6.5, it's going to go from 25 to 20, okay, from 20 to 15, okay, from 15 to 10. That's what the atmosphere is doing. All right. So let's take a chunk of air that is pushed upward. We talked about 4 different reasons a chunk of air would want to rise, okay? One of those lifting mechanisms, okay? And let's say there's no condensation going on. It is going to cool at the 10 degrees Celsius per 1 kilometer, the dry adiabatic rate. It's going to go from 25 to 15, okay? 15 to 5, okay? So now with regard to stability, the reason this is called stable, at every elevation, we have actually 3 elevations if you want to count the ground floor. Okay, we have an elevation at at the Earth's surface, we have an elevation 1 kilometer, and we have an elevation 2 kilometers. If you compare the temperature of the chunk of air versus the temperature of the air it's rising up into, okay, here there's the same, okay? But notice once it goes up 1 kilometer, notice that our chunk of air expanded and cooled to 15, okay, at 10 degrees Celsius is what it cooled. And notice that the air around it is 20. So if you're like me, you have to chant 15, 20, 15, 20. So can you see where our chunk of air is cooler than the air it's rising up into? Okay, it's not a hot air balloon sort of situation there. Okay, it would want to sink left on its own. Not to say we can't force it up, because there's lifting mechanisms that can force that chunk of air to go up. Notice at the next kilometer what's happening. Okay, now it's 5 versus 15. Definitely cooler. That's why we call that chunk of air and the atmosphere around it, that's a stable situation. All right, so the tendency is down. Okay, well, there must be an unstable situation out there. So, we're going to talk about absolutely stable, absolutely unstable, and conditionally stable. All right. So you'll have absolute stability if you send up a weather balloon, and if your weather balloon says that, like this says, if your environmental lapse rate, your ELR, is less than your WAR, okay, then it's going to be absolutely stable. I'll show you why that is. You can lift your chunk of air and it will cool, okay, but you're going to have it's going to have to be stable. Okay, your chunk of air will be stable. And I'll show you what that looks like. Okay. So I don't know if you can tell it, but actually when I reveal this whole thing to you, you're going to see actually this is the frontal wedging sort of lifting mechanism that they've chosen to show this for. All right. This figure is talking about an atmosphere and a chunk of air rising that is actually stable. The atmosphere and the chunk of air rising is stable. Okay, so there's our cold air mass hugging the ground. There are warm air masses over here to the left. The environmental lapse rate they chose actually is 5. Here's where they basically switch from a wet adiabatic rate of 5 to wet adiabatic rate of 6. I read just this afternoon that it can be anywhere from a wet adiabatic rate of 4 to 9.5. So our author chooses 5 and then it chooses 6. If you go with a wet adiabatic rate of 6, then 5 is clearly less than 6. Okay? All right, so we send up weather balloons. I like how these figures do it. Along here is kind of the profile temperature of the atmosphere. Okay, so it goes from 20, minus 5 is 15, minus 5 is 10, 5 is 5, 0, negative 5. Okay, so that's what the atmosphere is doing. Then we have our frontal lifting going on. So here's our chunk of air. Okay. Well, here's my little note that says that actually wet adiabatic rate of 6 here. Okay, the lifting condensation level, can you kind of see a little bit of cloud here? I'm thinking the elevation or level at which condensation occurs, I'm thinking 2,000 meters or 2 kilometers. So it goes from 20 to 10, okay, 20 to 10, no condensation, the dry adiabatic rate. Okay, and then actually it looks like it can go up 1 more kilometer, 1,000 meters, and then it's going to go to 0. That's cool. You see the beginning of the clouds. Now, like I said, you're going to have to switch gears, and I'm going to put in parentheses a wet adiabatic rate of 5 and 6. So here we go. It goes from 0 to negative 6. And negative 6 to negative 12. And then negative 12 to negative 18. Yep. Okay, so sometimes students say, well, how do you know that's the wet adiabatic rate of 5 or 6 instead of 10? Well, because you see there's cloud there, okay? So you have condensation going on. All right? So beside it in blue actually is a comparison of at that elevation with the temperature of the environment over here. So actually, early on, you know, this is cooler 5 degrees, this is cooler 10, it's cooler 11, it's cooler 12, it's cooler 13, okay? 13 degrees compared to the environment, according to that weather balloon we sent up. So its tendency is to, not to say it won't be lifted up, because we have frontal wedging going on here. But it's absolutely stable. So with each of these figures, I think this is kind of neat. Your author has this little graph over to the side. And the purple line there is what the weather balloon said. So the purple line is basically saying kind of the cooling as you go up in elevation. Along the bottom is temperature, and it kind of goes up here to the left. Okay. And then those other lines are, the red line is basically no condensation happening, and the blue line is condensation happening. So this one right here is what is the temperature of your parcel of air. So basically, if this temperature of your parcel of air is to this side cooler than your air, than your environment, then it's going to have the tendency to fall. So this was just my proof. I thought I was going crazy the first time I went with this textbook. So here's a figure we had earlier. Okay. And here's the more recent figure. So just to kind of, I haven't circled anything yet tonight. So this is the wet adiabatic rate of 5, the wet adiabatic rate of 6.
So if we have a question like a test with that, or like in our homework, will it always say the worst 5 or 6 or like 9.5?
Right.
Okay.
Yeah. Either that, or if I don't catch it, I'll give it to you
Later.
either way. No, either way. You go either way. Yeah. So let me just go back, though. And I want to emphasize this. Okay, the three different types of the environment. So this is kind of what it's distilling down to. The title of this is Absolutely Stable, or Absolute Stability. And the condition for being absolutely stable or absolutely unstable, or what was that last one, conditionally stable? The key is your weather balloon. The key is the environmental lapse rate, the ELR. Okay? So basically, what this says is if your ELR is less than ELR, it needs to be less than WAR. And you just need to know what those stand for. Okay? If that's the case, you get a chunk of air moving up and it's still going to be stable. It's absolutely stable. Okay, so then we go fast forward a few slides. Okay. Absolute instability, absolutely unstable, it's the same thing. I hope we're okay with that. Absolute instability. I'll just put ABS, instability. That will be the case if your ELR, oops, make sure I get this right, is greater than your dry adiabatic rate. And I'll go ahead next to the wet adiabatic rate, I'll go ahead and put 6 kilometers, or 6 degrees Celsius per kilometer, and the dry adiabatic rate is 10 degrees Celsius per kilometer. Okay. So I have a figure to go along with this one too. So absolute instability, absolutely unstable, that's what we all want, right? We want to, if you basically your atmosphere is unstable, then that means it's like, whoo, it wants to rise. And we'll talk about why that is. If your weather balloon, if your environmental lapse rate is greater than 10 degrees Celsius per kilometer, that's what's going to be the case. basically your atmosphere cools pretty quickly, and your chunk of air is going to rise and cool too, but it's not going to cool as fast. I think that's how that goes. All right, so here we go. Absolute instability. So what kind of lifting do we have here? It's not frontal. She's looking back at your choices. How many people think it's convective lifting? Yeah, looks like the sun is kind of shining down there. That's what I think too. Okay, so needs the environmental lapse rate. The weather balloon needs to be greater. Tell us that it's greater than 10, and they're going with 12, which is cool. That 12 is greater than 10, right? So what the weather balloon told us then is it went from 40. 40 minus 12 is 30, 28. Okay, 28 minus 12. All right, you get the idea. Okay, so those are getting cooler, 12 degrees Celsius for every 1 kilometer. All right. So I see clouds. You see clouds? We must have some sort of, it's actually only going to cool, it's going to cool at the dry adiabatic rate for the first 2 kilometers. Okay, it looks like the particular moisture content of that parcel of air, the dew point temperature must be about 20 degrees Celsius. Condensation, lifting condensation level. So it cools from 40 to 30, even from 30 to 20. Now if we go with 6, what's it going to cool to next? From 20, it will cool down to 14. Very good. From 14, it will cool down to...
Maybe I missed it.
Go ahead.
The temperatures are changing with elevation. Will those temperature changes be this? See, I can't even ask the question. I'm trying to think.
Are you talking about these temperature changes over here?
Yeah.
Okay, good. Yeah, that's just kind of we talked about before. If you climb a mountain,
2,000 meters, it's gonna. I mean, that elevation level.
is that where we're going to get clouds? You mean?
Yeah. I mean.
Well, it depends where we get the clouds. That lifting condensation level, where you begin cloud formation. That depends on how moist your chunk of air is. If it was drier, for instance, it might not cool to reach saturation until another kilometer. If it was drier.
Okay.
Yeah.
So then your temperature is going to be different then also up there.
That is the temperature of the air, and these are the temperature of the parcel of air that's rising. So those are the temperatures of the parcel of air that's rising and expanding. This is the temperature of the atmosphere around it.
So from 2,000 to 3,000, you're not always going to have a 12-degree spread.
Right.
You could have a
Yes.
20-degree spread, theoretically, on a certain day.
Right. But, and maybe it's
I mean,
not.
it's saying 12 degrees every 1,000 meters.
Right.
But theoretically, it could be 20 degrees every 500 meters, depending on the day.
Right, exactly. And that's why, since the stability of the atmosphere the ELR stands for what is your temperature profile as you go up. That's what the environmental lapse rate is. So that is what the difference
Theoretically, is it possible to have cloud cover at, and I'm just going to throw numbers here, at 1,500 meters?
Yep.
And your cloud, and your surface to your cloud cover at 2,500, your temperature is 26 or 28 degrees.
Yeah.
But then you go back above that, and it could be warmer and then go cooler again, and your thermal.
That would be an inversion. That's a temperature inversion. If you go higher and it starts to get warmer. Yeah.
Okay.
Basically, you have a pocket or a layer of warm air that's causing that, and that happens too. But that's good. So what your author has done is at every elevation. So I'll go ahead and so from 14, if it's still condensing, it's going to cool 6 degrees, and so it's going to go to 12, right? Or sorry, 6 degrees. It's going to go to 8. Can't do math. Okay. So at each of those elevations, if you compare your cute little parcel of air versus what it's rising into, okay, your parcel of air is warmer. So it's like your hot air balloon. Okay, your parcel of air is warmer, so that means it's buoyant. Okay. All right. So
Maybe I
that's
wasn't even
what.
making sense.
What's that?
And maybe I wasn't even making sense.
No, you were. I think it was a good question. But I want to emphasize this ELR up here. Okay? So the environmental lapse rate is greater than the dry adiabatic rate. And that will give you absolute instability. Okay, so over there to the right, your author's done the purple line, which is showing you the temperature of the atmosphere. And then those two segmented lines, the red and the blue, is the temperature of the parcel of air. And in all cases, it's warmer then. Okay. So we have one more, conditionally stable. So it'll be conditionally stable if your weather balloon goes up and gives you an environmental lapse rate that is between basically 6 and 10. Okay. So if your ELR is greater than your wet adiabatic rate, but if it is less than your dry adiabatic rate. Okay, so basically that puts it on both sides, and I do think we'll probably go with the 6 degrees Celsius per kilometer. Okay, it's greater than that, but it's less than 10. Then it's going to be conditionally stable.
So does that like hardly ever happen?
No, that.
Or is that like,
Well, you figure, and the conditionally stable part is it moist enough to begin condensation? That's the condition part of it. So the condition is, I'm going to put humid. I'm going to put humidity. Because humidity just means water content. That's the condition. I'll show you what it's saying here.
it's really that's a lot of stipulations.
Yeah, I know. It's like, yeah, you're right. The more stipulations, like, can that really happen? Yeah, it can. Okay. So the condition is whether it will begin condensing or not. And so I'll kind of show you that. All right, here we go. So we need something between 6 and 10, and so your author chose 9. So you can see it's cooling 9 degrees Celsius for every, this is the atmosphere. And it looks like we have frontal wedging again, lifting a chunk of air, forcing it upward, cold air and warm air. So if it starts at 40, it's going to cool at the dry adiabatic rate. You can already see kind of the clouds there. Your author does a kind of a good job. He puts the pink is where it's the dry adiabatic rate, and the blue is where it's the condensation's occurring, so it's going to cool at 6 degrees Celsius for every kilometer there. The blue actually means that the tendency right there is to actually sink. If you compare those elevations with the outside temperature, these are cooler. This is cooler just a little bit by 1 degree than this. This is 2 degrees cooler. If it's forced to continue to rise, now it's going to cool at 6 instead of 10. So it's going to go from 20 to 14 to 8. Okay. And then at some point in there, at an elevation of 3,000 meters, its tendency switches from being stable to being unstable. That chunk of air now is warmer than its surroundings. So its tendency would be to rise instead of fall. Okay, so again, we have an ELR, environmental lapse rate, that is between the wet adiabatic rate of 6 and the dry adiabatic rate of 10. So it makes it conditionally stable. And yes, this will be on your test in one form or another. So it's interesting. So to kind of look at what the profile temperature looks like, these look really close together, but if you look closely, you can see there's a crossover right here-ish, okay? In this case, you know, we have the parcel of air is cooler, and up here, we have the parcel of air is warmer. Cool. Ah, I know. So if you're like, if that just makes your head spin thinking of those figures, if you just remember that, you'll be fine. Put that on your note card. I know kind of what it means, okay? Clouds, we're kind of segueing into chapter 5, actually. Clouds are beautiful, okay? So with all this stability, okay, or instability, we have actually two broad types of clouds. I'll go ahead and put the word stratus here for these, okay? And we'll talk more about this in chapter 5, but these are stratus clouds. Okay, basically stratus clouds form when the chunk of air has reached its dew point temperature. The chunk of air has basically condensation going on, but your chunk of air is stable. It doesn't want to rise to the moon. It's just being forced upward little by little. So stratus clouds are those flat ones. Okay, they're shallow and they're flat in general. Compare that to clouds that form in unstable air. Okay, so these clouds would be your cumulus sort of clouds. Cumulus is the general name, and they kind of take off of that. Okay, but these are the ones that are nice and fluffy. Let me see. Usually clouds, especially if they are kind of new clouds, have nice flat bottoms at the lifting condensation level, and these would be nice and fluffy. So speaking of clouds, I'm going to show you a little video before we take a break. And that'll kind of introduce you to cloud types. So make my job